Salutations! This is the Biostats course Special Topics Talk number 12, Advanced Power Analysis, Into the Weeds. I'm Mark Williamson for the DaCCoTA project at the University of North Dakota. Our goal today, our destination as it were, is to trek out into the weeds to wrangle advanced power analysis. We'll start with the fundamentals, aka tapping into the roots, then hike past a basic overview, leaving alone any methods that are easily done. Pause to view the thorny gorge of difficult problems that prick my side and yours. Then traverse our way down that gorge to deal with them, turning our floundering into flowering. Finally, on our way out, we'll witness a collection of additional resources, released like seeds on the wind for future growth. This will be great. Now, before moving on, please take the pre-test, and you can also follow along with the R code as well. Beginning with the roots, why run power analysis at all? Well, the answer is before running an experiment. Say you want to compare a control and a pesticide plot. We've got the control here with no pesticide and a pesticide plot in B. You want to ensure you have enough samples to detect a true effect if it exists, because you're trying to ask the question, does the pesticide effectively inhibit growth? Power analysis can help determine appropriate sample size, whether it be 3 or 300. However, not all situations call for power analysis. For example, sometimes you want to do something else. If you're using an already generated data set, like a publicly available data set, etc., the sample size is unchangeable because generating the data is already in the past. Now, on the other hand, maybe you're working with a limited set of data, like rare cancer patients, or examining a proof of concept with a pilot study that you only use maybe like 12 as a rule of thumb. And finally, there may be situations like working with animal models where you don't know what the effect is going to be, to use the resource equation instead. The resource equation, this is pulling a quote from the paper, How to Get Sample Size for Animal Studies, talks about the resource equation. It's when you can't assume about effect size or get an idea about standard deviation with no previous finding, or if you have a really complex design, this is a good use for that. It helps you get a good ballpark of animals per group without doing too few animals, that is not finding a true effect if it's there, or too many animals and wasting animals that you don't need to. And another thing here, here's some examples of sample size formula for ANOVA designs that the paper mentions. You can see here that K is the number of groups and then N is the number per group. So depending on design, you will have different amounts. Okay, so you've decided you need to run power analysis. Here are the core components. We have sample size, effect size, significance level, and power. And these are all sort of interrelated. So if you know any three, you can calculate the fourth. So to get sample size, you need to know power, effect size, and significance level, also known as alpha, and you can get sample size. But that's not all you can do. If you have sample size, effect size, and alpha, you can determine the power of your study, and so on and so forth. So typically, power and alpha are predetermined, set to the defaults of 0.05 for alpha and 0.80 or 80% power. So the real challenge usually is determining the effect size. So what is effect size? Well, it tells you the strength of your statistical test. For example, when comparing two groups, the effect size gives the magnitude of difference between the groups. So a small effect size means a small difference in means, while a large effect size over here shows a large difference between the means. And now the variability in the measures also play a role. So you see these are tighter, where the ones down here, more variance in these distributions. And how this plays out is the smaller the effect size, so down here, the larger the sample size needed to detect this true effect. You see, it's hard to parse out the difference. You need to pile up a lot of samples. Whereas if there's a large effect, you only need a lot fewer samples. So to actually calculate effect size, you can either estimate by turning to past data and essentially getting something like a test statistic out. You can look at similar studies that have done it and do the same thing, or even use simulation. Otherwise, you can essentially guess at it, or estimated guess. There are default values for small, medium, and large effect size for a variety of statistical methods, as shown here. And if you want, you can also check out my other videos I've done on power analysis for more examples of specific tests. Let's practice some basics while we're here. So for a t-test, the effect size is denoted by d and is the difference in means divided by standard deviation. So mean difference, standard deviation. So starting out in G power here, I've entered two means, 5 and 6, and the standard deviation of 2 within each group to calculate a certain effect size. Replicate it by hand here. We see that that's going to be, okay, I got 6 minus 5, 2. That's going to be 1, 2. So 0.05, same thing we got here. And plugging it in, we get a sample size of 64 per group, or a total of 128. And this is with the default alpha, power, and then allocation ratio, so the ratio of numbers between n1 and 2 as 1, so they're same group size. Okay, that was pretty easy. For ANOVA, effect size is denoted by F. It involves eta squared, this Greek letter here, which is the ratio of an effect's variance and total variance. So we can show this here. So this is variance divided by total variance, effect variance. Another way of putting it also is the ratio of the effect sum of squares divided by total sum of squares. And that's more helpful if you're actually doing like ANOVA and getting tables out. So in G power, the variance explained is 5, and then the within group variance is 30, and which means the within group is not the total variance. So if we add these together, the total variance is going to be 35. So to do this, write this out, we're going to do square root. It's going to be 5 divided by 35 divided by 1 minus 5 divided by 35. That's going to give us, I'll go up over here, square root of 1.143 divided by 0.857. Just going to give us a square root of 0.1667. Whoops, 0.1667. You can follow on with a calculator if you'd like, to give us a total of 0.408, and that matches what G power gave us. This will give us a total sample size of 63. So since we had entered 3 groups for ANOVA, 21 per group. For regression, effect size is denoted as F2. There are 2 formulations depending if you want to determine deviation from 0, as shown here, and then played with deviation from 0, or if you want to get fixed model R squared increase, that is the difference between a model with and without the certain variable. In our case, it's variable B here. Variable interest, so we have the model with all the other variables shown by A and B, and then the model with not without B. So in the first case here, R squared is just a multiple correlation, squared multiple correlation, so that's going to be percent at 0.25, so 0.25, 1 minus 0.25 is going to be 25. 0.75, and that's going to be 0.33 repeating, same as here, and given 3 predictors, alpha, beta standard. That's going to give us a total sample size of 37. Now for the other case here, I want to make sure we know what we're doing here. So the variance explained by special effects, so very little from B, but this isn't RAB. So the R squared AB is going to be 0.42, and then the R squared A is going to be 0.4, because essentially the residual variance is 0.58. So to get that, to get RAB is going to be 1 minus 0.58. That's going to be 0.42. That's where we get that. And then since the variance was only explained for 0.2 without B, you just subtract 2 from here. Anyways, so how this is calculated out for the F2, we got 0.42 minus 0.40. Again, that top variable is essentially the variance explained. We get that number back of 0.02. And the bottom here is 1 minus 0.2. And again, we get that residual variance back. That's what the bottom is here. If we divide those two, we get 0.034, which is capitulated up here. Again, in this case, I actually set the power to higher, 0.95, kept the alpha the same, and the total sample size needed to be 451. If I bump the power down to 0.80, this would have driven down the total sample size as well. Those basic examples are all well and good, but what if we stand on the precipice of more complicated models? How do we deal with the thorny issues of repeated measures ANOVA, generalized and mixed models, longitudinal data and survival analysis, and structural equation and latent class mixed models? Well, let's find out. Repeated measures ANOVA involves group measured across time. So here's a schema of 3 groups across 4 time points. And there are 2 major distinctions: between factors, or between effects, and within factors, within effects. Between factors tests if there is a difference across groups. So that's going to test if group red is different from group yellow and group green. On the other hand, within factors test if they're different across times, across repeats. Say, is there a difference between baseline, time 1, time 2, and time 3? And of course, you can have the interaction as well, looking at both time and groups. So I ran repeated measures ANOVAs before in both GPower and R using the package WebPower in an earlier iteration of power analysis, but I ran into some issues with getting the same numbers out. Thankfully, I had very useful feedback from a viewer who helped me out on that front. It turns out that in WebPower, the effect size is needed. So this is a scaffolding of how to enter in GPower and WebPower. Anyways, for WebPower, you actually needed to multiply the effect size that you would normally add into GPower by a coefficient called C. For between factors is calculated like this. We have K is the number of repeats, and then rho here, this P, is the correlation between repeated measures. So you need to take that and add it. So in GPower, if I add typical alpha power, group number, measurements, correlation, just 0.05, and effect size, I get a total of 102 samples. Now to do the same in WebPower, I add this stuff, but then I need to calculate C, which is going to be the square root of 4 divided by 1 plus 4 minus 1, and then 0.05. That's going to give us 1.26, and we can multiply by that here. It's going to give us 99.4, so we need to round up to 100 because you can't have half people. But then also, since we're dividing by 3 groups, we need to have this number rounded by, divisible by 3, so we'll bump it up to 102, so that is good agreement between them. Great, we have agreeing sample sizes. What about within factors? And again, you need to divide by 3. Well, easy enough. This time the coefficient C for within effects is going to be this here. So we can calculate and get 2.83. And in G power it gives us 24 and web power gives us 23.23. So bump it up to a whole number, 24. Great. That worked out pretty well. Now G power and web power are great, but it's not the only way to calculate sample size. Because getting effect size from ANOVA is often esoteric, as you have to run often have to run ANOVA, get a sums of square estimates anyways, pull them out, run them around. So why not try simulation? Package Superpower does just that. It has the added bonus of nice plots to distinguish what you're attempting. So here is a 3x3 design given from the reference number 6 on Superpower. There are 3 groups labeled as factor B and 3 time points, factor A. All of them have the same mean except one, which is 25. And standard deviations are all the same, set at 5. Plotting the results here shows, it's really nice, it shows all the means, and then you see the one here bumped up. And you can run power here, and then you can actually get power curves, which is really nice. So applying the design of results show to detect a within factors difference. So that's across time, or factor A. You need 44 samples per time would be needed. The same was true for between factors, so or factor B, you needed 44 per group. Looking at both groups and time, so the interaction, sometimes known as within between, you needed 28 per group and time. So this was good and well and good, but what if I want to do my own? So I created my own design. It's a 4x3, so 3 groups by 4 time points, sort of like I had that schema, and adding a little more changes here than just what they had. And naming them repeats in groups. So here's what the plot looks like. You see as group 3 increases over time, group 2 decreases over time, and group 1 stays the same. Running this here, it turns out, because essentially all averages out across time at the end, no amount of sample size would give me power to detect a difference because there wasn't one across time. But within groups, I only need 15 per group to detect it, and for both, the interaction was 35. Right, we've covered more advanced ANOVA. Now let's bloom against some advanced regression. Standard regression is also labeled as a general linear model. So that's a general linear model, also known as LM linear model. Now a generalized linear model is for non-normal distributions like Poisson or logistic, and you call it generalized. If a random effects are added, a linear mixed model is used in reference to the mix of random and fixed effects. Finally, a generalized linear mixed model incorporates mixed and generalized model elements. Now, I've included how to do this in both R and SAS because I do a lot of R, but I do a lot of my generalized models in SAS. However, for sake of time and sort of proficiency, I will just look at the R tools. Package power and package simmer. But you can use proc power and proc GLM power in SAS if needed. Okay, how does this look like in practice? Well, general and generalized linear models with PWR power look identical. U is the number of numerator degrees of freedom, so that's the number of groups minus 1. V is the denominator degrees of freedom, which you'll see in a second. So adding 2 and dividing by that gives the number of groups. We're using 2 groups in these models here. So if we run this here, power calculation, we see here, there's that, V, and to get the actual, so this is, again, denominator degrees of freedom. To actually get sample size, we're going to round this, but we're going to add V plus 2 divided by 2, and we get sample size per group of 1 97. For linear mixed models, we have to turn to package simmer, which uses simulation to calculate sample size. Here's an example from reference 8. The model includes sentence and ID as random effects. That's how you set them up in R here. And group, sentence type, and word order as fixed effects. There are a total number of 480 observations. For sentence and idea, there are 24 and 20 groupings. So when we run these, initially power is well below 80 for both sentence and ID. So you can achieve higher numbers per random effect to determine how many you need. You essentially extend the model to theoretically include more number of sentences or more number of IDs, so those are individuals. And then you can run these power curves. So in the case of sentence, we had 24, so somewhere around here, pretty low power. But if we bump it up to about 80 words per sentence, that goes above the 80% power mark, so that would be good. For ID, it's a little shakier here because we didn't do a lot of simulations, but somewhere between 90 and 120 is needed. Again, I show more examples of how to use simmer with power analysis in other talks I have done. A generalized linear mixed model is going to be very similar. Using reference number 8, again, we have this model. The difference here is that now it's, instead of normal, it's binomial. The conditions are 200 observations, subject and item are random effects, and condition is a fixed effect. 10 subjects, 10 items. The model does not have power as is, so we're going to extend. So first we could extend the number of items. If we get up to 35, that's good. If we extend the number of subjects also to 35, it looks like that good. But we can also extend both at the same time. So for example, say we set items to 30 and then looked at the difference in subject we see here. So here, item is already increased to 30. And then if we start increasing subject, we see that if we just hit 15 subjects with an item set of 30, we can get enough power. So there we go. Well, that was helpful. Let's turn to more time. We've covered time before in repeated measures of ANOVA, but what about a more general longitudinal data sets? Well, package long power is here. Here are some general examples given by the long power documentation. So there's a lot of things you enter, so I'll kind of walk through this. So delta is the change in pilot estimate of the parameter of interest. So it's essentially something like an effect size. There is t, the sequence vector of time points. There's also going to be beta, another essentially proxy for effect size that we'll see later. That's going to be the estimate of the placebo effect, so the slope or rate of change in the outcome. So sig2i is the pilot estimate for the variance of the random intercept, so variance in random intercept. Sig2s is estimate of variance in random slope, and sig2e here is pilot estimate or residual variance, so different variance estimates pulled out here. And the COVSI is the pilot estimate of the covariance of random slope and intercept. And to calculate this, we're taking in the same thing of these other values, square rooting them and multiplying them by 0.80, and then power is 80. In the first example, we want sample size, so we input this delta. And what we get out here is n with a sample size of 207 per group, because there's 2 groups, rounded up to 208 as a whole number. Again, n is total sample size and n is sample size per group. So in the second example, we have n, but we want to calculate delta. We can do the same thing, and we can see here that it's really going to be the same, other than rounding errors, because these two procedures were inverses. One had delta that wanted sample size, other had sample size and wanted delta. Otherwise, all the other values were the same. And then finally, in this third example, say we want to use beta to sample size. We're going to get the same as before, 208 per group, because a beta of 5 here was equivalent to a delta of 1.5. We can also add in a full model. Here the example pulls in sleep study data. So we have the function LMER, so reaction as a function of days, and then this is random slope and intercept in here, and then we can plug this model into here. Percent change is the percent change in the pilot estimate of the parameter of interest. Time sequence, we pull this out, we get rounded up to 69 per group because we had 2 groups, control and treatment. Now, an alternative way of describing the same model using function LME will give the same outcome. Now, if we did just a random intercept only, gives a sample size per group, plug this in here, of 18.5 or rounding up to 19. And if we switch to a random effects model that is instead a generalized estimating equation with an exchangeable correlation structure, the structure has a similar but not identical sample size of 18.8, but it actually rounds up to 19 anyways. You see there's subtle differences in how these things are working, but it comes at about the same. Here is a more specific example on Alzheimer's that builds all the coefficients. The variances are set here, so random intercept, random slope, residual variance, we've seen this before, but more just building out as objects, covariance, and then we're going to get this cov t, has a function that enters these variances, etc. T is our vector of time points, n is our length of t, and then we're going to make these marginal model working correlation matrix, taking in values and using from the function above. Again, some of this is a little detailed, so look at package long power for better information. But essentially, you're using this to get a correlation matrix, and you can plug this into this this method for calculating sample size. It's from DaCCoTA. And you enter the delta, t, and then the r. This is why we did all this work too. This is this correlation matrix, same significance and power, and we get 4.14 or 208 rounded up samples per group. And if you use Eggland, you don't need an r. You just enter in some of these ones we calculated, the sig2s and the sig2e, and it'll give us the same thing. So maybe it's easier to just run something like this rather than going through all the work to get this R. But you can. Now, for a very particular time-based method, survival analysis, I found package PowerSurvEpi, so Power Survival for Epidemiology, to have a lot of useful tools. Starting out with determining deaths required in Cox proportional hazard regression with 2 covariates, we generalize a mock data set. As per the example code, x1 is group 1, x2 is the other, with 0s and 1s denoting survival and death. Running function numDepi, we find we need 70 deaths. But what about total sample size? Well, we'll set the proportion of subjects that die, just over 50%, divide by the deaths to get a total of 137, using the ceiling function round up to a whole number. So we need a total of 137 to witness the 70 deaths. Okay, here's another useful function, PowerCT. Pulling in data from OPH, so that's an ophthalmology data set where NE is the number in the experimental group and NC is the number in the control group. And RR is going to be our postulated hazard ratio. So when we pull this out here with 200 per group, the power given out is only 0.63, so that's not good enough. What if we boost the group size up to 250 each? Well, it's closer, but not great, so let's do a third one and boost up to 300, and great, we got just enough power, which is these code just calling it. Okay, so that was great, but what if we want to, instead of trying out sample size to get the power we want, it would be better to enter power and get out sample size. And of course, we can do just that with another function, SSICT. We can flourish with that. In this case, we have the same formula of the survival analysis by group. And now we just add power, as well as this K. It's the ratio between the experimental and control group. Since we want equal group size, this can be 1. And lo and behold, it pops out 294, very close to the rough estimate we got from above here with 300. Rounding out our thorny problems, I selected structural equation and latent class mixed models to cover. Structural equation models because they are a standard example of multivariate analysis, and then latent class mixed models because a viewer had asked about it once. So for structural equation models, package Superpower looks equipped to deal with such things. I'm not very adept at structural equation models, so this will just be a cursor layer look. Using function Superpower a priori with an effect size of 10, an effect measure of what they call RMSEA, which is root mean square error of approximation, gives a sample size of 42. Using an effect measure of FO, so the population minimum of the maximum likelihood fit in function gives a much higher 4.07. This is unsurprising because it turns out there's the relationship between RMSE and FO is that FO equals degrees of freedom times RMSE squared. So to get the equivalent measure of FO that we want, so degrees of freedom is 100 times 0.10 squared. That's going to be 100 times 0.01. So that's going to give us 1. So if we plug that in here for an effect size of 1, we're going to get ourselves the same observations of 42. Now it also gives this graph by default here, but what's even more, using a very wordy function called Superpower.PowerPlot.by_n, we can get curves. So because the RMSEA and FO are the same, gives the same power curves. They're identical. You can see here at about power 0.8, the sample size is about 42, like we saw in our calculation. So the answer is life, the universe, and everything. Now there are other effect measures that can be used beyond F0 or REMSEA. MC, GFI, and AGFI are all listed as well in Superpower, so go wild if you know what those mean. Latent class mixed models, a method I also know very little about, but since someone had asked about it in the past, I wanted to dig in a little bit. I wasn't able to find any article, but I did find a paper that simulated various designs. Reference 15, a paper called Recommendations on the Sample Size of Multi-Level Latent Class Models. Here are some patches from the paper. Here's one. When designing a study, one common question is, what sample size do I need? Unfortunately, there is no standard or simple answer to this question. Boy, that is the truth. Okay, moving on. They ran simulations using models with different group numbers, samples per group, complexity, distinctiveness, and number of indicators. The design yielded 384 simulation conditions by crossing the 5 factors as previously described. Okay, so they covered a lot of ground here. Here is table 2, which gives minimum sample sizes per group across differing distinctiveness. So they had 2, high and low. Indicator, 2 categories, 6 or 12. Number of parameters, 2 categories again. Groups, they had between 6 groups between 10 and 100. And then they called what? Complexity. Yeah, low and high. You can see here it goes from anywhere to 5 to over 100 depending on the scenario. So this gives a rough estimate to go by if you kind of understand your broad model you're going to be doing. More precise estimates, I'm afraid, will require trekking out beyond what even I can do, where the plants have no names. Well, we've covered a lot of thorny issues, at least in brief. I focus on R due to its wide application and high degree of specialized packages. But if you don't work in R, power analysis is still within your reach. First, there are a variety of online calculators that you can plug in numbers like effect size, power, and alpha to generate sample size. I also mentioned SAS previously, which has a good power analysis functionality. SBS does also have basic power analysis methods. Stata appears to have a fair number as well. The same goes for Minitab. Now, I've only passed the knowledge of Stata and Minitab, but if they're your go-to statistical software, give power analysis a try. When it comes to R, there are many other complicated models that I couldn't cover in this talk. I'll leave you with some other packages that you can explore yourself. First is a list from reference 2 with a handy set of purpose descriptions. We've already sort of covered power serve epi and long power, but you can take a look at the other ones here. Additionally, next there are R packages I found that have the phrase power analysis in either the name or description. And these don't include ones we already cover or reference. We have from Ttest to Superpower. And finally, I found a list of packages that have power in the name or description and appear to be power analysis related. Again, not showing earlier ones. So I have 21 here to be precise, from Bayes count to past. We're not done yet. Oh no. Here are another 21 from Farm POW all the way down to WMW POW. In total, it turns out there are over 50 packages of power analysis in R. We just covered the most common ones. And again, for more information on how I generate lists like this of R packages and their descriptions, you can check out my Exploring R Packages introduction video. To summarize what we talked about in this talk, power analysis and sample size calculations are fundamentals for proper experimental design. Calculating effect size is a huge part of it. It can be tricky to understand what's to do for advanced experimental designs, but never fear, there are better methods to just do that. Please take some time to fill out the post-test and survey before you go. Here are references that I use throughout the talks. These are 1 through 11, and here are 12 through 21. There should be links in the description as well. Pulling up that last dandelion, please reference the DaCCoTA project if you found this training useful to your research. Thanks, and have a powerful day.